Hello everyone, this is the 7th and last lecture on colligative property under the chemistry of dilute solutions, and the topic which is going to be discussed today is abnormal colligative property. So there must be some abnormalities in the values of colligative properties, and in what situations this is going on and how to find out this abnormality, the extent of this abnormality. We are going to discuss all these things in today's lecture. So let's have a look on some facts where some these types of situations are arising out. So it is sometimes observed that the value of molecular mass deduced from the colligative properties does not agree with the expected value. That means, suppose you are determining some molar mass from the observation of lowering of vapor pressure, elevation of boiling point, and you know the concentration of the solution, no exact number of particles dissolved in the solutions, but you find some abnormal results. That means it is deviating from the theoretical value. So this is one case, and discrepancies arise out when the solute molecules are present in the associated form or in the dissociated form in the solution. That means these types of discrepancies actually arise out if there is something else happen with the solute particles after dissolution. What happens now? They may get dissociated into more than one particles, or they may combine to associate to form a single species from more than one particles. So in these two situations, these types of abnormalities arise out. So this can be actually determined, this value can be determined with the help of a factor which is known as the Van Hoff I factor. So let's discuss on Van Hoff I factor. This is actually the observed molecular mass divided by the theoretical molecular mass. Now this molecular mass is calculated from the observation of the colligative properties such as lowering of vapor pressure, elevation of boiling point, depression of freezing point, and osmotic pressure. Okay, so from any of these experiments you are deriving the results experimentally. So observed means experimental results and theoretical means the calculated results. Okay, and therefore you can say that experimental value of the colligative property and calculated divided by calculated value when the solution behaves ideally. That means there is no association, there is no dissociation. So this ideality is actually no association nor any dissociation, and this is actually the ratio of actual number of particles divided by the number of particles if it behaves ideal. That means for no association or dissociation, this is the number of particles in the denominator, and in the numerator the actual number of particles after association or dissociation. Okay, so in terms of the different colligative properties, they may be written as I equals to the boiling point elevation observed, boiling point elevation calculated, that means experimental by theoretical, freezing point depression observed by freezing point depression calculated, lowering of vapor pressure, relative lowering of vapor pressure observed divided by relative lowering of vapor pressure calculated, or osmotic pressure observed, osmotic pressure calculated, or the observed molar mass divided by the calculated molar mass. So this is actually, this ratio is I. This may be greater than 1, this may be less than 1. If it is greater than 1, so you have to expect that there is dissociation taking place, and if it is less than 1, you have to expect that association is taking place. Okay, so let's start from dissociation. So here is the situation where the particle gets dissociated after dissolution. So let's say the particle is an electrolyte and which has the chemical formula stoichiometry AXBY. So it dissociates into X number of Y positive particles and Y number of BX negative particles. And if the initial concentration of AXBY is C, then if its degree of dissociation is alpha, that means the fraction of the whole part of the molecules that those are getting dissociated, that fraction is alpha. That means if half amount of particle is dissociated, then the value of alpha is 0.5. If 1/4 amount of particle dissociated, then the value of alpha is 0.25, or 3/4 amount of the particles are dissociated, then the value of alpha is 0.7. So this way alpha is the degree of dissociation. Okay, So if C is the concentration and alpha is the degree of dissociation, then alpha part has been dissociated out of the whole part, which is unity. So 1 minus alpha is the fraction that is remaining undissociated. And if the concentration is C, then at equilibrium the concentration of the undissociated part is C into 1 minus alpha. So if alpha part is getting dissociated, though, so that should be C alpha, and since the stoichiometry is X, so it is X C alpha for A, Y positive, and for B X negative it should be Y into C into alpha. Okay, so these are the exact number of particles present in the solution at equilibrium after dissociation. It may be fractional dissociation, it may be complete dissociation, or it may be no dissociation. If it is no dissociation, alpha is 0. If it is fractional or partial dissociation, alpha is 0 to 1, and if it is complete dissociation, then alpha is equal to 1. So what is the total number of particles at equilibrium? Now the undissociated molecules plus the dissociated molecules. Okay, so undissociated molecules have the concentration number of particles C into 1 minus alpha, and the dissociated number of particles for the cation it is X C alpha, and for the anion it is Y C alpha. So this is the total number of particles. So if you take C as common here, then 1 minus alpha remains, and X alpha plus Y alpha, and from here if you take alpha as common, then you will get this expression C into 1 plus alpha into X plus Y minus 1. Okay, so the expression of I is actual number of particles divided by number of particles if it behaves ideally. So in the numerator you have put this value, and in the denominator if it remains undissociated, then alpha equals to 0. In that case the overall number is C into 1 minus 0, that is C, and these values are 0 since alpha is 0. So C is the actual concentration. So the experimental value of the concentrations, that means the actual number of particles divided by the number of particles if it behaves ideally, actually this is divided by C. Okay, so in the numerator you are putting this value, and in the denominator you are putting only C, and after cancelling each other we get this expression. So we have the expression of I 1 plus X plus Y minus 1 into alpha, and therefore after rearranging we get the we also can get the value of degree of dissociation. So with the help of I, that means abnormal colligative property, you can also find out the degree of dissociation for these types of electrolytes. Okay, so this is one of the applications of Van 't Hoff factor I. Okay, and the alpha is the expression I minus 1 divided by X plus Y minus 1. Okay, now we have the expression I equals to 1 plus alpha into X plus Y minus 1. Number 1, if there is no dissociation, that means alpha equals to 0. In that case alpha equals to 0, so I equals to 1. Okay, so that is observed value are in agreement with the calculated results. That means no dissociation, so the value of I is 1. That means the theoretical value and the calculated value are same. And finally, when complete dissociation takes place, that means if alpha is equal to 1, if complete dissociation takes place, then 1 into X plus Y minus 1, 1 cancelled, so X plus Y remains there, so the value of I becomes X plus Y. So in that case I equals to X plus Y. That means the colligative property is X plus Y times higher than the calculated results. So if it is sulfuric acid, then the value is 3. If it is calcium chloride, the value is 3. If it is sodium chloride, the value is 2. Okay, so this way you can calculate this value. If it is say calcium phosphate, then the value is what? 3 plus 2. That means the value is 5, isn't it? Yeah, the value is 5. 2 phosphate and 3 calcium, so the value is 5. So it should be 5 times greater. Okay, so I discussed one example with one example. Suppose arbitrarily for each mole of an electrolyte, say calcium phosphate, the boiling point elevation is 0.1 degree Celsius. So the water boils now at 100.1 degree Celsius. Okay, so if complete dissociation of calcium phosphate takes place, then what should be the boiling point? Now it should be 5 times greater. That means 0.1 into 5, not 100.1 into 5. It should be 0.1 into 5. 100 plus 0.1 into 5. That means right now the boiling point should be 100 0.5 degrees Celsius instead of 100.1 degrees Celsius. Okay. For calcium chloride, it should be 100.3 degrees Celsius. For sulfuric acid, it should be 100.3 degrees Celsius. For sodium chloride, it is 100.2 degrees Celsius. For glucose, it is 100.1 degrees Celsius. Because you know that colligative property is such a property which only depends upon the number of particles and not on the chemical behavior of the particles. Okay, so here you will count just the number of particles, and it is one more thing I would repeatedly say here, that boiling point is not at all the colligative property. The colligative property is actually the elevation of boiling point, the boiling point which is deviating from the original value. Here the deviation is plus 0.1 degrees Celsius. So from that 0.1 degree value we have to multiply the I Van factor I for complete dissociation for the salts or other things which we have mentioned as examples here. Now association, in case of association, if n number of A molecules associate to form A whole n species, a single species, then their respective concentrations in terms of degree of association is this one. C into 1 minus alpha is the unassociated form of A, and the associated form of A has the concentration actually alpha by n into C, that means C alpha by n. Okay, so what is the total number of particles? Total number of particles is the summation of these two, C into 1 minus alpha plus this one, and if you take C as common, then it becomes 1 minus alpha plus alpha by n, and then after having taken alpha as common and putting the value this one in the numerator and C in the denominator, you will get this result. Okay, we haven't taken alpha here as common because it's not necessary at all. Here we are taking alpha as common. Okay, so C cancelled by each other, and then the value that remains in this equation, I equals to 1 plus alpha, we have taken as common, alpha into 1 by n minus 1. Okay, therefore the value of alpha has also expression I minus 1 divided by 1 by n minus 1. So with the help of I you can find out alpha, or conversely with the value of alpha you can find out the value of I. Okay, and special situations is alpha is 0 means no association, alpha 0, so I equals to 1. Okay, and the values are in agreement with the calculated results. And number 2, when all the particles associate, that means in that case alpha equals to 1. If alpha equals to 1, so it is 1 plus 1 by n minus 1, that means equals to 1 by n. So I equals to 1 by n. So in that case the colligative property is 1 by n times higher. Actually it is lower. Okay, 1 by n times higher means this is a fraction. If the value of n is 2, then it is 0.5 times higher than the calculated results. Okay, for example, in case of acetic acid, if it completely associates to form a dimer, then the value of 1 by n is 1 by 2. It is 0.5. So 0.5 times higher means actually the value lowers. Okay, in that case, for that solution, say the water solution, which was boiling at 100.1 degrees Celsius for a glucose solution, particular amount of glucose solution, so same amount of acetic acid if dissolved, then the boiling point would have been 100 plus 0.1 by 2, that means 100.05 degrees Celsius. Okay, so this way you have to calculate the deviation. And try to calculate the values of Van factor I for a glucose, sulfuric acid and acetic acid solutions having some same concentration, provided alpha equals to 1. So if there is no association or dissociation, alpha equals to 0 for glucose, but for sulfuric acid alpha equals to 1 means it forms 3 particles, and for acetic acid alpha equals to 1 means its degree of association is 1, that means it is completely forms a dimer. So in those cases, say C is the concentration of each solution, and for glucose it neither associates nor dissociates, so number of particles equals to its concentration into Avogadro number into 1, because it is neither association nor dissociation. But in case of sulfuric acid, dissociation takes place in order to produce 3 number of ions, that means 3 times more number of particles here. So here the number of particles is concentration into Avogadro number n into 3. Okay, and in case of acetic acid, 2 molecules associate to form a dimer. In that case number of particles become halved. that means it becomes 0.5 times. So C into N0 into half. So what should be the values of I? The values of I should be, in the first case, I is 1. That is, it is completely in agreement with the calculated value. The experimental value is completely in agreement with the calculated value, whereas this is 3 times higher, and this is actually half times higher. Okay, that means the value lowers. So that's all about abnormal colligative property and about the last lecture up on this chapter. So thank you and have a nice day.